be fluorescent everywhere. All right, phosphorus. All right, 5 to 10 micrometers. Atomic number, high atomic number, conversion efficiency. We talked about this already. We talked about those. But you can take another picture. Yeah.
No, we did.
Yeah, we
You did?
Oh, we did.
Yeah, I told you. That's called phosphorescence. It's coming a little bit later, but it's coming. All right, the atomic number, high atomic number preferred. This will increase the likelihood of the X-ray photon being absorbed, right? Isn't that what we want?
Yes.
We talked about that when we talked about what type of interaction we talked about this.
Photoelectric.
Exactly, photoelectric effect. Okay, you want a high atomic number so the X-ray can be absorbed. Okay, the higher the atomic number, the greater the chance of the X-ray being absorbed. Right? Yes?
Yeah.
Say yes, please.
Yes.
Okay, so it will increase the likelihood of the X-ray being absorbed. Okay, so that's why the high atomic number. The conversion efficiency. Let's take a look. This is the ability of the phosphor to emit light in response to X-ray stimulation. I told you all this before, but I'm just repeating it on the screens. But before I force you to write it down.
Why did we care at this point if the X-rays absorb?
Because if it was not absorbed, if it's a low atomic number, the X-rays will just go right through, and they will not interact with the phosphor.
But they might still excite it, right? Or,
No.
oh, so we want absorption.
We
or
want
excitement.
absorption, exactly.
Okay.
If it doesn't absorb, because remember, and this is kind of related to what we're doing in 415. If the X-ray is just going through, okay, nothing happens, right?
Oh,
It's not
okay.
interacting with anything. So you want it to interact, you want it to be absorbed, okay? Because when it absorbs, it can give off its energy. In this case, it's good. In the case of tissue, it's not good, because you're giving the patient a dose. And you're exciting the atoms within the tissue, which is not good. But you want it to be absorbed, in this case. Yeah.
So, so if you increase the KVP, the photon would have a very less likely chance of interacting with any matter. Just hit the IR, it'll show up black. Okay.
All right, and when you do screens, you provide a measurement of the screen, how well they are able to convert the amount of energy that they absorb into visible light is called screen speed. Let me repeat that. The ability, okay, of the phosphor to absorb the X-ray and turn it into light is called the screen speed.
Password.
The screen speed is, I'll tell you in a different way. Screen speed is the ability of a phosphor to convert X-ray energy into light energy. And so there is a measurement, right? Because you're not using the same elements, and you're using different combinations of amounts of phosphor. Okay, and so some screens are, and we'll talk about this later, but some screens are said to be high speed, some screens are said to be low speed.
So that's screen speed.
Okay, and that's what it refers to. And so if I say a high speed screen, what is it? What do you think I'm saying?
Higher ability.
Well, faster.
It's like, that means it's like fluorescent.
It's saying that it's able to absorb, okay, very little energy and convert it into light. Okay, slower screens, they need to absorb more. Okay, and so with slower screens, you will need to use a little more radiation. Okay, because they need more to absorb. You following me?
Okay.
Okay.
Yeah.
All right. Faster screens, they don't need as much radiation. They, with a little bit, they absorb that and boom, they emit a lot of light. Okay. The problem with that, depending on how you're seeing it. The problem with that is resolution. Faster screens provide you less resolution. The resolution is very, very poor. Slower screens provide good resolution. All right, the conversion efficiency, okay? Increased conversion efficiency decreases patient dose. And this is referring to the speed still, okay? If you have a fast screen, you decrease patient dose, right? Okay, but what's the downside? Resolution. Okay, good. The spectral emission, precise wavelength of light emitted by the phosphor. Precise to what? Precise to the film, what the film can absorb. Okay. Let's match film spectral sensitivity. I said it before. So, luminescence, luminescent light in response to stimulation. I said that before. So, two types, right? Phosphorescence, fluorescence. You already wrote it down, so don't rewrite it again. Okay. One revolution about the nucleus will take 10 nanoseconds. I didn't want to give you that information, but since it's there, now you memorize. 10 nanoseconds. That's how long it takes for one electron to go around the nucleus. 10 nanoseconds. If it takes longer than that, then it's what?
Phosphorus.
Phosphorescence. There you go. Ooh, screen lifespan. Screens typically last between, depending on the use. If they are heavily used, maybe 5 years. Maybe 5 years. After that, all of them start to lag. Okay? And that's not a good thing. You don't want it, so you gotta get rid of it. Okay? If they are not used a lot, maybe 5-7 years is a good lifespan. All right, the phosphors. Let's look at the phosphors. All right, these are some examples of the different phosphors that have been used. Zinc sulfide, if you were using low kVp. Barium lead sulfate, if you were using high kVp. Calcium tungsten. Okay, and this is one that we're going to see a lot. We're going to see a lot of calcium tungsten in the design of image intensifier for fluoroscopy. DR uses calcium tungsten, so they're used quite a bit. Okay, and here are the rare earths that I pointed at you before. So some of the compounds that are used: gadolinium, lanthanum, and yttrium, the three that I pointed at you before. Okay, so these are the old ones. Okay, calcium tungsten came after. Barium and zinc. Calcium, all of them were old. Okay, that'll be easier to do that. And then in the early 70s, we got the gadolinium, lanthanum, and yttrium, and they work very well. So we're gonna describe in just a second. I'll describe what's the difference between the two. Okay, monofossil material. Okay, there is an improvement over calcium tungsten. Calcium tungsten are the oldest of all. Okay, and this is what Edison used. Okay, now calcium, everything is compared to calcium tungsten. Calcium tungsten receives at a speed of 100. Write it down. Speed of 100. And so remember when we talked about filters, we said what is the equivalent in filtration that we use? What material? Always aluminum, right? Always compare it. We said we compare. If it's copper, we compare it with aluminum. If it is concrete, we compare it with aluminum. In this case, every comparison, every screen is compared to calcium tungsten. Okay, even though calcium tungsten I never used calcium tungsten screens. Okay, by the time I became a technologist, they had already been. They were still around, but I never used them. They were not popular anymore because the rare earths were so much better. Okay, so monofossil materials, the rare earths, there is an improvement over calcium tungsten. The absorption ability was better. In most cases, I'm talking in general terms. We're not going one by one and comparing yttrium and lanthanum and gadolinium, comparing each one. No, in general. Okay, if we bulk all the rare earths and compare them to calcium tungsten, we can say the rare earths have a better absorption ability, okay? The intensification factors were better. The conversion efficiency, we're gonna talk more about conversion efficiency. This is the ability, absorption ability is the ability to suck up the X-ray energy. The conversion efficiency is how much of that energy that it was absorbed, how much can you release it as visible light. Okay. So red Earth increases speed without compromising much resolution, I would say. It's not you're compromising much resolution. Okay. At least you're not compromising it to the point that it's not of diagnostic quality. Okay. There is loss of resolution, but you're not compromising the ability of the radiologist to do a diagnosis. Remember, last time I was telling you, you know, the naked eye can see what, 10 lines per millimeter approximately? And if you're showing 100, what's the point? Your eye is not going to be able to see it, right? So, and that's what you were getting with direct exposed film. With rare earths, you know, you can do about 5 lines per millimeter, 7 lines per millimeter, which is very good. I mean, it's pretty good. What do you think computerized systems will do? What do you think they fit? Do you think that they have better resolution or worse resolution?
Worse.
All of them have worse resolution. All of them. The best they can do is about 3 lines per millimeter.
Wow.
Yeah. Yeah. And those are the really good systems, the mammal systems, about 3 lines per millimeter. But they have other qualities that help in improving other areas. Better contrast, better, you know, brightness, all of that. And you can manipulate it. So that, all of that have some advantages. But when it comes to strictly resolution, it's not better. All right, and so with, in general, what you have with intensifying screens, specifically with rare earth screens, is that you have a decrease in patient dose. Okay, that's the most important thing, decrease in patient dose. All right, so let's take a look. Let's compare calcium tungsten versus the rare earth. Okay, just to give you a hint, okay, of what's going on here. All right, when it talks about conversion efficiency, take a look. The conversion efficiency of calcium tungsten is between about 5% efficiency. So out of all the X-ray energy that is absorbed, only 5% of it can turn into light. Okay. So not very efficient. Rare earths, on the other hand, take a look. They can absorb, they can convert, not absorb, convert. They can convert between 15 and 20%. That's very good. In comparison, I mean, it's still very inefficient. You want it to be 40%, 60%, but we don't get to that. Christina? No?
That seems inefficient.
Yeah, very inefficient. Very inefficient. These are not good systems, but that's what we have. All right, screen speed is a relative number that describes how efficiently X-rays are converted into usable light. Okay. And we use something called the intensification factor. Okay, and it's related to the conversion efficiency of the phosphor. This is what I was describing to you before. Okay. Meaning what? This is, okay, what is their ability to convert whatever light they get? What is their ability to turn it into visible light? That's what this is saying. Okay. So, the intensification factor, if you want to measure it, if you want to give it a numerical, if you want to have a numerical sense of what it is, okay, what you will do is you will do an exposure required without a screen divided by an exposure required with screens. Okay, so this number will always be a lot higher. So what you do is you make an exposure. Okay, you have an ion chamber where you're going to measure how much is coming out. You have your phantom or whatever you're using. Your phantom, make an exposure and see how much exposure you need. Okay, and then you do the same but this time you're gonna use it instead of just plain film, okay, you're gonna use an intensifying screen and film and measure how much it was required to make the same exposure. This number, once again, will be always higher, will be a lot higher than this one, okay? Because the screens, that's the purpose of the screen, to minimize patient exposure. Okay, and that's how you get the intensification factor. Okay. Descriptive rating, you always talk about par speed and high speed. Par speed is there's different ways of doing it. The par speed is your standard, and then you have high speed, and then you have the very low screens. But in this case, I think Bouchon or Carl, I can't remember, one of the two, just use, I think it's Bouchon, par speed and high speed. Okay, par speed is always 100. Anything above that is high speed, according to this definition. However, when you talk to technologists that use this type of system, they will tell you, for example, the extremity screens, even though their speed is 200, they call it a slow. But it should be slower than the other screens, because the other screens, when you're doing chest x-rays, abdomens, their speed is 400, 600, 800. Okay? Are you following me? But according to this definition, what did I say par speed was? 100. So
100.
anything above 100 is considered to be high speed.
Okay.
So it's all related to what is the technologist comparing it to. Most technologies, I mean, there's a few old timers that still they use direct exposed films. Very few of them left them, but they do, and so they know what we're talking about. We're comparing it to the very, very slows. Okay, when they had 100 speed, the calcium tungsten. Okay, yeah, but anything above 100 is really high speed. But be careful, because if you're talking to a technologist, they will compare it to their extremities. Okay, and their extremities, screen speed was 200. Okay, so even then it's high speed, but they're comparing it to their abdomen screen. Some of you are looking very funny. Does it make sense what I'm saying, guys?
Yeah.
Really, some of you. I know you're tired, but hang with me for another 5 minutes. Come on. Yeah, Garrett.
So for the intensification factor, the IF portion, so in order for good conversion efficiency of the X-rays to light, you need the screen to be higher than the exposure, you're saying. Is that what you said first?
Higher than the exposure without the screen? Is that what you're saying?
I kind of lost the part where the screen should be higher than the exposure. That's what I got. And
Let me describe how you will do this experiment. Okay? So you grab one of a phantom, right? Say you have a hand phantom, okay? And you have a phantom, and you will have a film. Then you have a film. No
intensifying screen?
no intensifying screen, just a film. So you make the exposure, and you like the film. Say, oh, this is a beautiful film. Yeah, look at it. Great detail, good resolution. I can see fractures. I can see everything. Yeah, I can see the soft tissue. I can see bone. So beautiful X-ray. We like it. So we're going to use the same technical factors. Okay. Say you use, I don't know, 40 mass, 4 kV. 40 mass and 50 kVp.
Okay.
Okay? Say that. What kVp is it? 50 kVp. Okay, so this is what we have. And beautiful film. We like it. So what we do now is we bring our ion chamber. Ion chambers are used to measure exposure. So now you're not going to measure the beauty of the film. You're going to measure how many and the strength of the X-rays. Okay? So you make the same exposure using the same technical factors, and you make the exposure, and you report a number. Let's suppose that number was, I don't know, just a number that just came to my head. 3.57 Rangens. Okay? 3.57 Rangens. That's the exposure.
Okay.
Right? Okay. So this number will go on top.
Okay.
Now we're gonna go and make another exposure, but this time we're gonna use intensifying screen.
Okay.
Same hand, okay, make the exposure. Oh, beautiful film, oh, you like it, you know, nice trabeculae, soft tissue, fractures, everything. But in this case, instead of using 40 mass and 50 kV, you only use 1.5 mass. Okay, and 50 kV. Okay,
Oh, okay, I understand.
all right. Now you go back and repeat the exposure, but using your ion chamber. Same numbers, okay? And you only end up getting, I don't know,
Oh, I understand
22
now.
millirentgen. Okay,
Okay.
and now this number is divided by this number.
Okay,
That
so
will
that's
give
an
you the,
equation. Thanks,
intensification
thanks.
factor. Make
That really
sense?
explains that section right there.
Good. What do you mean you guess?
No, I get it. I'm saying I get
Oh,
it.
you get it, okay. Everybody? Okay? Yeah? Okay, so that's how the intensification is good. That's what I remember I said, this number will always be a lot higher. Always have, it has to be a lot higher. Otherwise, then you're defeating the purpose of using intensified screens.
Yeah.
Okay?
Yeah.
All right, let's stop here. We'll go early today.
Okay.